So today we are going to talk about the addressing modes. So the classification of instruction set architecture based on the addressing mode. So in our previous session, we looked at the syntax of instruction set architecture for different classes of instructions like arithmetic instructions, memory instructions, and branch instructions. And then we have seen the example, even using the CPU simulator tool, that how the ISA classification based on the operands location, whether they are in the register, whether they are in the accumulator, whether they are in the stack, or one operand from the register and one operand from the memory. So finally, we looked at the register-based instruction set architecture and register memory-based instruction set architecture with an example. So next is how those operands will be accessed if they are in the register, if they are in the accumulator, if they are in the memory, then how they are going to be accessed. So the accessing the operands we call the addressing modes. How they are addressed. So the addressing mode specifies how operands are located from memory and or the registers. So there are some common addressing modes which apply to any instruction set architecture. So the first one is the register addressing mode. So in the register addressing mode, and we'll see these addressing modes with an example. Okay. The second one is immediate addressing mode. Then register indirect addressing mode. Fourth one is displacement addressing mode. Fifth one is indexed addressing mode. Then direct addressing mode. And memory indirect addressing mode. Then auto-increment and auto-decrement addressing mode. And scaled addressing mode. So these are the common addressing modes. Right? So we'll see this one by one with an example to understand. Okay. So we'll see this one by one now. So the first one is register addressing mode. So in the register addressing mode means when an operand is in a register, that we called accessing that operand from the register is known as the register addressing mode. Right? So I'll just give one or two addressing modes example using our simulation tool to better understand. Okay. So let me just quickly try to share that screen. Just give me a second, please. Okay. So now, suppose if the operation, just recall that if the operation is like R1 is equal to R2 plus R3, that means the source operand 1 and source operand 2 both are from the registers only. So the instruction the addressing mode instruction is add R1 is the destination register, R2 is the source 1 operand, R3 is the source 2 operand. So in this instruction, what is the addressing mode of second operand? Then we can say that the second operand is in the register R3. So let me just show you the example on the simulation tool. Okay. Just for understanding this addressing mode. So let me share the screen here. Okay. I hope my screen is visible, right? Perfect. Yeah, good. So now just see here. Let me just edit the instruction. See. Yeah. So now see here, the first operand 5 is moved into the register R0 and second operand is moved into the second register. So in the execution unit, if you look at here, okay, if we fetch that instruction from the main memory into execution, so the instruction is move 5 into R0. When it is decoding, they find the operation code is move, and when it is executing, you can see that nothing is happening. So in memory instruction, it is just moving the value, the copy of the value from the memory into the register R0. Similarly, when the second instruction is executed, when it is fetching from the main memory, and when it is decoding, it says that it is a move instruction, and moving the operand 7, okay, moving the operand 7 into the second operand, that is R0 register, right? So here it says that in this instruction, when the operation, add operation is executed, when you fetch it, okay, when the add operation is executed, when you fetch it, the value 7, that is the immediate value, and the register value is here. So here you can see that for any operand, there are the addressing modes: immediate addressing mode, the register direct addressing mode, register indirect addressing mode, memory direct addressing mode, memory indirect addressing mode. Similarly for operand 2 also. So just to give the visible, it says that both the operands are from the, let me just reset all this. Okay. And let me just remove the program instances. So remove the program. So then just create a program to better understand, add that program into the test, then add the instruction, create that you're just moving the value 7 into a register like R0, then move the value, suppose 5 into a register R1, and then the actual operation will be take place, that adding the value that is from R0 with the R1 value and store the result into R1. So then when executing this, okay, in the execution unit, when you see this, select the first one, fetch the instruction, 7 into R0, then decode the instruction. So there is nothing is here. The value is moving into the temporary register R0. So then after executing this on the hardware complement, the 7 is moved into the register. So source 1 operand is in the register. So when executing the second instruction, when it is fetching, the value 5 will be moved into the R1 register. So decoding it, it says that the value 5 is moved into R1 register. So after the operand 5 is moving into the register R01. So after executing this, the R1 value is set to 5. So then executing the instruction, add instruction, when it is fetching and decoding that, you can see here the register, the value, second operand is in the register. So what is the addressing mode? Register direct addressing mode. Here also the value is in R1 register, that is the register direct. So this mode we call the register addressing modes. Right? Does that make sense to understand? Yeah. The next one is immediate. In the immediate addressing mode, the value will be available within the instruction only. So when an operand is a constant value within the operation, then the addressing mode is said accessing that operand we call immediate addressing mode. For example, if the operation is R1 is equal to R3 plus 3. So this means the second operand is directly given within the operation. We call this static value also. So the instruction for this immediate addressing mode, or within this instruction, we can say that what is the addressing mode of second operand? That means we can say that it is a immediate addressing mode. So the instruction is add R3 plus R plus 3 and store the result into R1. The next addressing mode is the register indirect addressing mode, also known as the register deferred. So mean to say that the second operand of the operation is a register, but that register holds the address of the operand. Which address? The memory address of the operand. So it is generally often used for the C pointers in the C programming language. So assuming that, for example, assuming that the address of the second operand in any operation is suppose in register R3. So then the operation in the programming language looks like R1 is equal to R2 plus the pointers, the address of R3. Can you guess what will be the instruction here? Can you guess the instruction for this operation? Based on its location. Yeah, Austin, perfect. Thanks for that, correct. The instruction is add R2 plus. The second operand is in the main memory. That's why it is written in square bracket. So in the square bracket, R3 is there. So R3 register holding the address of the main memory, where the operand, the value is stored. So this you call register indirect. The register is not having the value, direct value. Register is having only the address of the operand. Does that make sense? Yeah, good. Thank you. The next, let's go to the next addressing mode, that is displacement. So this displacement addressing mode is the offset we called. So accessing an operand whose address is computed based on a base address and an offset that we call the displacement. So for example, to show this, to understand, in the main memory, when the program is stored in the main memory, okay, so that main memory is a block or collection of blocks of memories, right? So we call this as each block of memory. So how these blocks are identified means the addresses. So what is the first block? The address of the first block is known as the base address. And if the element is at some other block here, and if we give the block name as block 1, block 2, block 3, block 4, block 5, and if this block size is, okay, the block addresses are given, then the base address is block 1 address, that may be like 000, and the next one is 002, suppose, second block. Next one is 004. Next one is 008. Next one is 0010, suppose. So then how it is computed? Base block plus the distance. So this we called offset or displacement. So this is generally this displacement addressing mode used for the local variables on the memory stack. If it is a memory stack, then the local variables will be, so where the base address is the stack frame pointer. That is the top of the stack, we say. Right? Is it clear? The displacement address. Yeah, wonderful. So if we practically see on our simulation tool, suppose, you can experience that which addressing mode is having here. Now, for this program, we have given the base address 100. So the next instruction, first instruction is at base address 100, the physical address. Next instruction is 6 bytes away. That is the displacement of second instruction. That is 100 plus 6 bytes. The next address is again 6 bytes away. That means 100 plus 6 bytes. So every block size is 6 bytes. Is that clear? What is displacement then? Got you? Good. Okay. Right. So in the theoretical example, we can say that, suppose, assuming that the base address, how to represent in the operations means, in the operations looks like, for displacement accessing address, the base address of the memory will be stored in one temporary register. Let us say that is in R3 register, and the element is in the 100th block from the base address, suppose. So then the actual address, the effective address of that operand is the address of the actual operand is base address plus the offset or displacement. So that gives the actual address. So in the operation in pointers, how do you write? R1 is equal to R2 plus address of the operand. Address of the operand. So what is that address? How it is computed? Base address plus 100. So in the instruction, when compiler converts this kind of operations, then the second operand accessing mode is the displacement accessing mode. So how it looks like in the instruction means it is an add operation. That is source 1 operand is R2, that value is in the R2. Second, source 2 operand is at this memory location. How this memory location or the effective address is computed means the base address is in the temporary register plus the 100, that is offset, that will be right into the square bracket. Is that clear? Good. Okay. So I would like your attention for this particular address. Okay. For this particular addressing mode, suppose, assume that R2 is equal to 5 and R3's base address is suppose 100. Okay. And the offset is, here the 100 is given, right? Can you please execute this instruction on the CPU simulation tool? I would like to pause this. Try to open the CPU simulator from your end and execute this instruction to perform this operation. R1 is equal to R2 plus the address. Can you please help me? You please perform the this operation on CPU simulator and share your screen, please. That will be recorded. So we will have 5 minutes time. In 5 minutes, please execute the sequence of instructions to perform this operation. R1 is equal to R2 plus the address. All of you please try, because your screen will be recorded after that. Okay. If you during execution, if you find any doubts or anything, I'm here to help you, so that it will be a great help to understand the addressing modes. Please do that. The second step is need to add the value 100 with the register R3, and the result will be stored in the R3. So then move the value. Suppose for R2, we have said that the value will be 5 in the R2 register. This instruction will be executed. And then add the value. The source 1 is R2 register, and source 2 is R3, and destination will be R3. So now the result is in R3. So move the result, which is there in R3 register, into the destination register R1. add instructions. Is that make sense? Are you all following this, please? Good. So just follow these steps and please share your screen. Okay, Leah, no problem. Yeah, probably Austin, Jonas, Abrar, Alexander, they will do it, I think. Even Rolando also. Like, Austin is, yeah, start executing Austin. That's great. Yeah. One more time. Austin, can you please share your screen one more? Yeah, it's looking good now. Yeah. Please go and try to execute the instructions one by one. So let us observe what is happening in the general purpose register. Yeah, first instruction. Good. Okay. Yeah, that is moved in the instruction register. Yeah, in R3, the address is computed. Good. That's wonderful. Yeah. Right. That's good. That's good. Thank you, Austin. But here, one thing we need to observe here is we just computed the what we called we computed the effective address, and that effective address that we need to provide the value also. Generally, when we use the program stacks, so in the program stack, it gives where the values are there. So here, these are the addresses which are coming that we will observe later. Probably in your lab also, you might have observed this one, right? So yeah, that's a good observation. Thanks, Austin, once again.
I agree. Okay.
Yeah. So let me. Good one. Yeah. So I hope all of you got kind of idea, right? What is displacement and how it will be executed. Good. Okay. So now let's go to the next addressing mode. The next addressing mode is indexed addressing mode. So this indexed addressing mode is very useful for accessing the elements in the arrays, in array of memories. So in array, the elements are sequentially stored into a sequence of memory. So again, the beginning address and the offset will be there, like in the displacement. So what is the difference between the displacement and this indexed means? The beginning address and the offset of the element are stored in registers. Both are stored in registers. So by just considering an example, suppose, assuming that the assumption here is the summation with the element in an array, which is at the fifth location. So x of 5, that means x is an array and the fifth element is used for adding with the source operand 1. So the operation is R1 is equal to R2 plus the array here. The array operation is given. So then what is happening in this array of elements? If the sequence of elements are arranged like it is a X array, so it is accessing the index. So beginning address is its beginning index like 0, 1, 2, 3, 4, and 5. So fifth element, suppose A, that will be used to add with R2 plus A. So then what is there here? This is the first beginning address and this one is the offset. So this beginning address will store in one register and this offset will be stored in another register. So it requires two registers. And the size of each index depends upon what type of array it is. If it is the integer array, then the size is 4 bytes. The size is 4 bytes. So assuming that here the R1 and R2 registers are used, so some other temporary registers used for storing this beginning address and the offset address. So let us assume that R3 register, which has the base address of this array, and R4 register, which holds the address, displacement or offset of the element. And within the program, if that array is declared as an integer type, it gives that how many bytes of memory reserved for one element. So where R3 holds the beginning address, beginning of this array. Let's set the beginning address of the array. So then how this offset is computed? Offset is the fifth element and each element size is integer type, that is 4 bytes. So it is multiplied as 5 multiplied with 4. So that is the offset that will be stored into R4 register. Then how the second operand will be represented in the instruction. So for this operation looks like, after compilation, this operation is R1 is equal to R2 plus the R3 plus R4, and here star is used. That is what? It is a base address plus the displacement of an array that is written in the bracket. So the instruction looks like, how it looks like? It is an address so that writes in the square brackets. So by looking at this instruction, it can easily identify that what is the addressing mode of this second operand in this instruction. So that we can say that R3 is holding the base address and R4 is having the offset of the element of the array. So this is an index addressing mode. So what is the difference between the displacement and indexed addressing mode? Means in displacement, the second operand is having the base address plus the direct offset value is there. But in indexed one, the offset is computed based on the size of the element. Is that clear? The difference between displacement and indexed addressing mode. Yeah, great. Okay, so now let's go to the next addressing mode is direct addressing mode. So the name itself says that when the memory address of operand is known at compile time, suppose. So that is the value of the address is known at the compile time. So typically used for loading the static or global variables in the program. So for example, by assuming that one operand is at the memory location, suppose 100 memory location, and source one operand is in the register, source 2 operand is at this memory location. So then the operation, okay, looks like the address of the second operand is this one, that is the address. So operation looks like R1 is equal to R2 plus the address of the operand. The address is directly given. It may be static variable or global variable. So then can you guess what is the syntax of the instruction? What is the syntax of the instruction for this? Add operation. Destination is R1, source 1 is R2, source 2 is address. That address is 1000. Is this clear? So if by looking at the instruction, you can say that what is the addressing mode of second operand, means it is a direct addressing mode. The address is directly given. The next addressing mode is the memory indirect addressing mode, also known as memory deferred. So when accessing the nested pointers in C programming language, the addressing modes are accessing those elements are like, the memory indirect addressing mode. So for example, assuming the first address of the element is in the temporary register R3. So then the operations looks like in the programming language that basically R1 is equal to R2 plus the memory indirect, means the memory block is holding the address of the memory where the element is there, and the R3 register which holds the first address, that is the base address. So base address plus the memory address is equal to the element actual address, we call effective address. So this part is computed as, the address is computed as star R3. So that is, this one is R3 and that is having the memory. So this one is star. So then the instruction looks like this: R1 is equal to R2 plus address only. But in the actual implementation, the instruction set architecture designed to execute such kind of nested pointers is add R1, R2 with the address, memory address of the address. So that will be written as et in R3 in the bracket. So if the second operand or any operand is in the instruction looks like at R3, that means which addressing mode is, it is a memory indirect addressing mode. Is that clear? Yeah, good. So if you look at the differences, the next addressing mode that we can look at here is auto-increment. Generally in branches or for loops, we use auto-increment and auto-decrement. So these auto-increments, they are useful when stepping through an array. So the address of current element is stored in a register as we looked. And this register is automatically incremented as the code proceeding to the iterate, because if it is integer type, the R1 suppose holding the base address, then if that integer type means it automatically add 44444, so that gives, try to access the sequence of elements. So assume that the beginning address of the array is in suppose R2 register. So that is, if there is an array that is integer type, the base address The starting address is in R2 register. Then the operations in a high-level programming language, that is the do-while loops or while loops. While the condition is true, what is happening here? R1, in R1 register, the element at the beginning address will be stored first. Then the next element will be stored. It is integer type. So in the next iteration, the next element is 4 bytes away from the base address. In the third iteration, 8 bytes away from the iteration. So it advances 4 bytes to the next element. So then the instruction, that is the loop instruction here. That is the loop instruction. So loop instruction, what is this? If you recall the instruction set architecture which we discussed, conditional jumps. So here the condition is there, then it is jumping to the next instruction, next element. So that gives add the element of R1, okay, where R1 is the destination. Add means load the element into R1. Okay. So the source again become the R1 only, base address. But from where this value is loading into this, because destination is this, adding this value. That is indexing part. So here the second operand here is, the second source operand is at R2 plus go to loop. It is a go to loop is the, this go to is the operator and loop is the true condition. If it is true, then go to this location which is computed here. So if it is auto-decrement, instead of going to plus, it will use the R2 minus go to loop. So this is auto-increment and auto-decrement addressing mode. And finally, the last one is the scaled addressing mode. So scaled addressing mode used to access an array element with the array's base address, but the element index and the size of the element will be scaled. Means what? If it is simply mentioned as x of, if it is simply mentioned as x of elements, and if it is integer, so that's a different. Scaled means the size of, it is requires 4 bytes. But scaled means instead of integer, the array is going to use the double data type, double of x of elements. So here again, one register is used. Suppose, for example, R3 used to store the beginning of the register. And for these elements, use another register for the, suppose R4, for the scaling purpose. Because the size of element is increased. So it can handle arrays with any type of, because the scaled one, it can handle any type of elements such as like characters, integers, float values, or doubles. So for example, assume that the beginning address of the array, as just mentioned, that in the R3 register, and the array is suppose double data type, the base register will be in R3, and the operation basically looks like R1 is equal to R2 plus the 10th element of the array. Then how it will be computed? R3 is having the base address, and the offset will be stored into the R4 register. So how it will be computed? The 10th element. So R4 is equal to the 10th element. And that is the address of the element 10. So then the operations looks like R1 is equal to R2 plus R3 base address multiplied with the element 10th element. So 10th element means how it will be computed then? The instruction looks like it is an add instruction. Source 1 operand is R2. Source 2 operand is base address plus the element. That is the 10th element multiplied with the double the size. So it takes 8 bytes. So this is the scaled addressing mode. It's a scaled addressing mode. So overall, by considering a case where an element, suppose instead of single dimension, if the element is suppose two-dimensional array elements, and the array is a double data type. So what it means, x of 10, 10th row and 10th column. So how it will be computed then? So in this 10th row, 10th column, the overall size of the array, so adding this, R1 is equal to R2 plus the third row, fifth column element. So then what will be the instruction for this? So to understand the instruction, to design the instruction for this, first need to understand the actual calculation of the element. So what is that? The location of the third row and fifth column is the base address of the array plus 240 plus. It is a double, so the fifth element it is, so fifth column, and the element size is 8 bytes. So mean to say that to justify this operation, how this 240 is computed. So third row, fifth column, that starts from the fourth row actually, because indexing from 0. So the first 3 rows occupies with how many elements? 10 elements. In each row, how many elements? 10 elements are there. So 3 rows multiplied with 10 elements, because 10 elements are there. And per row, each element size is double. So that is row multiplied with 8 bytes. So that is each element size is 4 bytes. So that is 80 bytes. 80 bytes multiplied with 3 rows. That is 240 bytes. So then the element, the fifth element is, calculate the column now. The fifth column is computed like, is the sixth element on the fourth row in two-dimensional array. When it is indexing from 0, 1, 2, 3, and 4, it is 0, 1, 2, 3, 4, and 5. How it is computed then? Each element size is 3 rows. Okay. After third row, fourth row starts. So it is multiplied with this one. So it will be computed as, it starts after the first 5 elements. So that is the fifth element 5 elements multiplied with 8 bytes. So that's the meaning. 5 elements multiplied with 8 bytes. So that gives the 6th element in the column. So in other words, the offset or the displacement for the 4th row is 240 bytes, and the index is 5 within the 4th row, and the element size is scaled with 8 bytes. So then again, assuming the beginning address, in this case, suppose the beginning address of this operation, the beginning address is in R3 register, suppose, and then compute the value in R4 register, which is multiplied with the 8 bytes, plus the offset is 240 bytes. So that gives the instruction like add R2, and second operand is the base address is in R3 register, and the 5th column element, so that is R4 holds 5 multiplied with 8. Why? Because it is a double type, plus the offset is the 3 rows away it is. So that is 240. So from here, this example covers the base address plus index multiplied with scale plus the displacement. So is the memory addressing mode used by 8086. So this addressing mode can replace or include most of the addressing modes so far which we discussed. So what are those? It's having the register addressing mode, indexed addressing mode, scaled addressing mode, displacement addressing mode. So that covers all the combination of addressing modes. All the combination of addressing modes. Is that clear? Yeah, wonderful. So this instruction gives how this will be implemented. So from this example, if you analyze that, how this instruction directs the arithmetic and logic unit to perform the operation. First, it is going to perform this multiplication operation. Then it performs the addition operation. Then it performs the next addition operation. Then it performs this next addition operation. Then it moves the result. Does that make sense now? First operation, second operation, third operation, then fourth, then finally 5. So total, the sequence of instructions, how it will be generated? Yeah. So for your understanding, let me just give that example. So what is the instruction? The instruction is add R1, R2. The second operand base address is in R3 plus the element size is in R4 multiplied with the operand because it is double size, so 8, and then adding the offset 240 in the square bracket. So the sequence of instructions are, if you observe, for this instruction, it directs that move the value 5, the element 5, okay, into the register R4. Then the instruction MUL will be multiplied with what? multiplied with 8 bytes with the element of R4, result will store into R4 now. So then it adds the R4, 240, that is immediate value, with the R4 and store the result into R4. Then adds the result, then adds the result. What is that? The R1 or anything like, R3 plus R4. That is the add one. So R3, R4. The next, it adds the result of R2 and R4. And then moves the value R4 into R1 register. Is that make sense now? The sequence of instructions which are used. Right. So finally, if you look at these instructions, in every instruction, you find either direct value or registers. Direct value or register. So what is the instruction set architecture means? It is a register instruction set architecture. Does that make sense now to understand the concept? Yeah, that's it. Okay. So in our, the coming assignments, in assignment, the theory assignment, I would like to share that with you. So the next topic is classification based on instruction length that we will discuss in the next class. But before going to release the assignment, theory assignment, I just want to give you the brief idea. Okay. So just we'll give the quick idea to understand what will be there in the assignment and how we need to address it. Okay, based on these addressing modes. Is that fine? Good. So let me just quickly share the screen with you. I think the screen is visible now, right? So this will be the assignment one, which will be released after the next class. But I just want to give you the brief about that. So there is a small C code is given here, okay, and we can find that this instructions which are generated from this is based on the 8086 instructions. Okay, so you can go through this tutorial material, but before going to that, I just want to give the complete idea so that it will be easy for you. So what we need to do, the prerequisite to review this one is to know that addressing modes. So when this small program is compiled on the Linux machine at Debian strength by using the compiler GCC and executing this code, it generated a assembly code here. Okay, it generated the assembly code. So what is the operation is here in this assembly code? The operation is, it is a for loop, suppose one loop. So in that loop, it is going to performing this operation that the buffer size is integer type. For I is equal to 0, what is happening in every iteration? The 5 is loaded into the array. Here B is the array, correct? Okay. So in this array, the first element at 0, 5 will be there. At 1, then 5 will be there. So this continues until this condition is filled. So in the main program, this for loop is calling, and then that for loop will be executed until the condition is true. So once this is executed on the GCC using GCC compiler, so it has given this code to me. Okay, you don't need to compile that program or generate this code. Okay, so in this code, the line of code is given here. So it find at which line the for loop is started means after generating the assembly code. Okay, so that's like the line 1, line 2, line 3, line 4. So at line 6, the for loop is started here. So then first what is happening in the for loop? The value 0 is moved. Then 5 will be moved. So it is pushing the value. So push operation is taking place in the stack. Then moving that value into the another register. Then doing the subtraction operation. Why? The size is 64 bytes. So every time when it is moving, okay, why? Because it is an integer type, right? Buffer size is integer type, so 4 bytes. So in every, until this buffer become full, this condition will be executed. So when it is executing, in every time, the subtraction operation will be happened on the array. So then the move the word, okay, the move operation, you're having this source 1 operand is this one, source 2 is 0. Then jump to the L2. That is, if the condition fails, it goes to the target, that L2 comparison operation. Because here the comparison will be take place. I is less than this. So comparison operation will be take place. So this is the overall instructions which are generated from the code. So what we have to analyze here, which line of code corresponding to the for loop, which lines of the code for loop. So at which line it is starting? The for loop starts at this, and the for loop is ending here. Isn't it? Does that make sense? Yeah, good. So then the second question asks that which register is used to hold the variable of for loop? Which register is used to hold the for loop? Yeah, that you need to identify from this. Then what is the memory address of the variable I of the for loop? So memory address of I, where it is there? What is the memory address? That is the data word that you find, memory address. So initially I is equal to 0, right? So moving the value, after moving this, the memory address, because anything is written in square bracket, that's the memory address. Correct? Then what is the beginning address of the array, and what is the addressing mode for the buffer size? Okay. In buffer size, what is the addressing mode is used? So it is an array, right? So what will be the addressing mode for arrays? Just analyze that. Then what is the addressing mode for the constant 5? Right? So that you need to submit this answer on Canvas only. You can download that PDF, but your answer will be submitted as like, quiz only. Just write the corresponding line code here, short answer, then select the correct, what you call the register here, select the, what is the memory address, okay, and so and so. Is that make sense? Yeah, EPB, correct us. No, 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 no. I'm just, oh, come on. Asking, you're motivated me to give the answer. Is that make sense? Is that okay? Yeah. So do you want me to release that assignment today or after next class? Because I think you are all busy with the, yeah, after next class. Thanks for that. Yeah. I think you all are busy with the current assignment, the lab assignment, right? Yeah. So what I'll do, I'm going to the pop-up quiz is there for addressing modes. I'm just going to assign it. Please complete it by tomorrow, whenever you find time. Is that fine? Is that okay? The due time. Yeah, okay. So that will be open for a whole day. You can complete either today or tomorrow. Only the 9 questions are there. That's all about our addressing modes, which we have discussed today. Yeah, Brad, by tomorrow you can complete it. Can anyone notice this? Austin, can you refresh the course page and check it out whether the dates are fixed or not? The pop-up quiz date. Austin or Ronald or Abrar, any one of you, please. Thanks, Austin. Due tomorrow before midnight. Yeah. Thanks, Austin. Okay. If any others are having any concern, anything about pop-up quiz or lab, please let me know. And now you are good to go. Before leaving, as usual, please give your good comments about the today's topic, good or bad, whatever comment. So that will help me to improve the course material. Yeah, thank you, Haley. Thank you, Abrar. Alan Rees, thank you. No, I hardly find your message after, you will be so active. What happened today? Have a great day. Thank you, Noah. Asking, thank you, Ranj. And thank you sharing your screen, volunteering for giving the demonstration. Jonas, to learn the instruction. Thank you, Jonas. Yeah. So thank you, one and all. See you in the next class. Thank you, Rolando. I appreciate.